is Astable Multivibrator using IC555 timer. So this is the last concept of this module. So here I already told there are two modes of operation in IC555 timer. One is astable and another one is monostable multivibrator. So astable multivibrator doesn't have any stable state. It keeps changing its state from low to high and high to low. I already told this. So after this is also called as a free running multivibrator. So because all or it will be called as rectangular wave generator circuit. So as you can see, I already plotted over here. So it is also called as rectangular wave generator or free running multivibrator. Okay, so this astable multivibrator doesn't require any external triggering circuit. So it will be because it is changing the state between two states. So here it won't require any triggering input. So to understand the operation, so I already told about the basic circuit. So the basic timing circuit. So this basic timing circuit will help us to know about this astable multivibrator. If you are perfect with this circuit, the previous series circuit, so this astable multivibrator is just an extension of the basic timing circuit, because I already told that for R in the basic timing we are operating manually by giving 1 or 0, but in the case of astable multivibrator, so instead of operating manually, we will be connecting one more comparator. So the comparator is nothing but an op-amp. So here we are using op-amp as an comparator. It is one of the application of an op-amp, as you already studied this in module 3. Okay, so let's start with an astable multivibrator. This is the circuit of astable multivibrator. Okay, so here you can observe there is no difference, much difference between the previous basic timing circuit and this circuit. So here you can observe the R is in the basic timing circuit, R will be operated manually, but here we are connecting one more LC. So, and you may think I already told why it will be called as a triple five timer. So why it is, you can observe we are using three 5 kilo ohm resistors. So we used three resistor, and three resistors are of the value 5 kilo ohm. That's why it is named as triple five timer. As you can observe the name IC triple five, because the values or three resistance of same values we are using. So the same plus VCC we are giving. So the range between 5 to 18 volts depend upon the applications, and RA, RB. So depend upon RA and RB, you can obtain sustained duty cycles. So maybe it is 50% or greater than 50% or less than 50%, depend on the values RA and RB. I will be also telling why depend on RA and RB, we will be getting sustained oscillations. Okay, so now first we'll start with the comparator. You can observe this UC is nothing but upper comparator, LC is nothing but lower comparator, and we are using SR flip-flop. I already introduced what is this SR flip-flop. Similarly, I'm using the NPN transistor, and it is denoted by T, and this will be the collector. Okay, so this point you can see this is collector, this will be emitter, and this is your base. Okay, so yeah, here you can you may have a doubt that what is this 2 by 3 VCC and this 1 by 3 VCC. Okay, so this will be as you can see, the plus VCC is connected here at this point, and after that here also it is connected to the negative terminal or inverting terminal of upper comparator, and in the next it is connected to the non-inverting terminal of the lower comparator. As you can see over here, it is connected to an 5 kilo ohm. When the plus VCC is coming across the 5 kilo ohm resistance, so the whatever the voltage is there, so some voltage will be dropped across the first 5 kilo ohm. So if there are three resistance, so only some amount will be dropped over that and remaining will be passed here. So that is how much it will be there. So out of 3, so it will be 2 by third of VCC will be at this point. That's why it is mentioned it as 2 by 3 VCC. So next the same 2 by 3 VCC will be again having one more resistance, and some of the voltage will be dropped here. When the current flows through this, some voltage will be dropped across the resistance. So the here it will become 1 by 3 VCC, 1 by third of the VCC. Okay, so in the lower comparator, you can observe this is a pin number 2. So here this 2, when the at this point this capacitor will start charging. If the capacitor starts charging, it will charge through the RA and RB only. So I will tell why it will charge through RA and RB. So first let's assume at this point it is dominating or it is more. So when the capacitor starts charging, so this point will be more, and that is the negative or inverting terminal is more than the non-inverting terminal. I already told when inverting terminal voltage is more than non-inverting terminal, obviously the output of the comparator, it will fall to the negative value. So when it will fall to the negative value, as per our assumption, when it is negative, we will be taking it has 0. When R is 0, logic R is 0 now. So here it is charging through the resistance, and here this point, at this point it will be more, isn't it? So this here the non-inverting terminal is higher than inverting terminal, that is it is dominating. The non-inverting terminal voltage is greater than inverting terminal at the upper comparator. So when this is the case, the output will be, or the signal will be in the positive. So when the positive signal will be there, so as per our assumption it will be 1. So now S will be equal to 1. When S is 1, R is 0, what is our output? It will be set. Set is nothing but Q will be equal to 1. When Q equal to 1, what about your Q bar? It will be automatically, it will be 0 because of complement. So then it is 0. So you can observe this is 0. That is what it is, 0. Okay, so when it is 0, Q1, this will becomes 1. So when this will becomes 1, the transistor here, it will be, this is the base of the transistor. So the IB, the current, the equivalent current will be generated, and when the IB starts increasing, whatever IC, it will also increases. As per the equation, IC is equals to beta IB. As IB increases, IC also increases. So when this IC starts increasing, so what happens? So whatever the current is flowing, so it will start flowing towards this, isn't it? So what happens again? The capacitors or the voltage at this point will start decreasing, and the capacitor will be discharged. Where the capacitor will discharge, it will discharge through the ground. Once the capacitor starts discharging, the voltage at this point will be less. So when the voltage at the inverting terminal, it will be reverse the case now. The inverting terminal will be, at the second case, it will be less than the non-inverting terminal. When this inverting terminal becomes less than the non-inverting terminal, obviously your output now it will becomes the positive value. When it will becomes the positive value, what is your assumption? When it is positive value, so I'll just change the color so that you can identify it. So now the R will becomes, now in the second case it will becomes 1, isn't it? So when R becomes 1, so okay, when R becomes 1, okay, I have to check this S. What is the value of S? When this point starts decreasing, okay, so automatically what happens? Then non-inverting terminal is less than inverting terminal. So obviously the output will becomes less. That is, it will get negative value. When it is negative value, the output will be getting 0. So when it is 0, S will be 0. Once S is 0, R is 1, automatically your Q bar now it will become 0. When Q bar is 0, whatever, sorry, Q is 0, whatever Q bar it will be 1. That's why you can see this is on. It is on. Okay, so next it is 0. When this becomes 0, whatever the current, it will be decreasing. So as it is decreasing, the collector is also decreasing, and finally it is almost, it is of the form of, it is not connected. Once it is not connected, what happens here? Whatever the voltage it is, or the current from this point, it is flowing, so across this. Okay, so at this point you can observe the RA. So instead of taking this road as it is, almost it is the current, collector current is 0. It is assumed that it is almost not connected. It seems to be not connected. The only path is to flow here, RA through RA and RB. Again, what happens? Your capacitor starts charging. Again, the same cycle will be repeated. Okay, the same cycle will be again repeated. So this is about the explanation of a stable multi vibrator. So again, once it starts charging, again the inverting terminal will be high than non-inverting terminal, hence it will be 0. So then it will be again 0. So this is about a stable multi vibrator. So let's see. So the explanation was given over here, on time and off time. So this is an and that is discrete, and this is just a schematic diagram of your astable mode. So as you can see, it will start charging. The charging will be from 1 by 3 VCC only. Why it is so? You can observe here, we are comparing this point with this point, that is it will start with 1 by 3 VCC only in this case, and the maximum it can reach is 2 by 3 VCC. So that's what we showed over here. This starts with 1 by 3 VCC and it will ends with 2 by 3 VCC. Okay, so then when it will start charging, when it will start charging, when the T on, that it is on. Okay, so then discharges when it is off. Okay, this is about a stable multi-vibrator. So this TC is nothing but charging time, TD is nothing but discharging time. The duty cycle is complete T on and T off. Actually, this is not T off, this is your T off. Okay, this is your T off. Okay, this is T on. So this complete cycle, off and on time, this is complete cycle. T on plus T off, that is a duty cycle. So let's see the what is this charging time value. I don't know what is the value of TC and TD. Let's derive that charging and discharging time. So I already told period of one cycle. So that is charging plus discharging is the total time period. So the frequency will be denoted as 1 over, that is always reciprocal of that time. So now the voltage across the capacitor. This is first we'll start with the charging time, that is on period. So the voltage across the capacitor is represented as VC. So that will be equal to VCC. So VCC is the main, you are giving plus 5 volts, isn't it? So that into 1 minus e raised to minus t by RC. So this R resistance where you may remember. So the capacitor will be charging through this RA and RB only. So this is nothing but this R. This R is nothing but that RA and RB. Okay. So similarly C is this one, the capacitor, where it will start charging and discharging. Okay. So here you can see the VC is equal to VF plus VI minus VF into e raised to minus t by RC. So this VF is your final voltage and VA is an initial voltage. So we are first calculating for charging time, that is TC. Let's see what is the initial voltage and final voltage from the figure. So as you can observe here, in the case of charging time, okay, so the initial value will be VI, isn't it? The initial, it starts charging here. The charge on the capacitor, so it will reach us at this point, right? The charge on the capacitor will be how, what? this 2 by 3 VCC. The final value, maximum value it can reach. What is the final value, the maximum value it can reach? It is VCC only, because whatever the supply you are giving, it is VCC, isn't it? So here you can observe in the figure. So the maximum value or final value it can reach is VCC. That's why VF is equals to VCC. Whereas your VI, initial value of for the charging will be 1 by 3 VCC, and the final value will be VCC, and the capacitor, the charge on the capacitor will be 2 by 3 VCC. Okay. So that's what written here. Okay. VI is 1 by 3 VCC. VC is equal to 2 by 3 VCC, and final value will be VCC, maximum it can reach. By substituting this value in the above equation. So what it becomes if I substitute the VC, VF, VI values. So see here, it will 2 by 3 VCC equal to VCC 1 by 3 VCC minus VCC. So as you are this time, I am calculating for which? Charging time. So replace small t by Tc. So then it is charging through. You remember the explanation I have given. So the capacitor will be starts charging through Ra and Rb. Why? Whenever the transistor will be becomes the internal. Okay, I'll show this only. So when this transistor is off, so when the transistor is in cutoff region, so what happens? There is no current across here. The only path it can flow is this path. So the current starts flowing here in this path, and it will reach the capacitor, isn't it? That's why the capacitor will be charged through Ra and Rb only. Okay, so that's why I'm taking in the during the charging and discharging, the resistance will be Ra plus Rb, and the charge C is the capacitor. Once you do the calculations, okay, so it will become minus 1 by 3 VCC minus 2 by 3 VCC into this. So after doing the calculation, you will be getting this. So how you got 0.693? So by the solving this, if you transfer this 2 by 3 VCC over this side. So if you transfer this side, what happens? This will becomes plus minus 1 by 3 plus 2 by 3 VCC, and E is there, log. So if you take that, you will be getting 0.693 VCC. Okay. This is the value will be going to get. So next is for discharging, that is off time. So the same equation, for this equation, let's see what is the final value, initial value, and the charge on the capacitor from the this. So I told already the discharging time. This is your discharge time, TD. So this is your TC. Okay. So this is TD. So initial value will be 2 by 3, isn't it? The initial value will be 2 by 3. The final it can reach will be 1 by 3, isn't it? The initial value VI, as you can observe in this, see, the initial value, it will be 2 by 3 VCC, isn't it? Then the voltage on the capacitor will be how much? The voltage will be on the capacitor. See here, voltage on the capacitor will be 1 by 3 VCC. Finally, what it can reach below this, the final value below 1 by 3, how much? So it will be obviously below this, it will be 0. Then the final value during discharge time, it will be 0. This is your initial value. This is your charge on the capacitor. The final will be less than this. That is nothing but 0. Okay. So that's what shown in this. Okay. So the capacitor voltage 1 by 3 VCC. Final value I told 0. Next, this is an initial value 2 by 3 VCC during discharge time. So substitute, and the T is replaced by TD because I am calculating the discharging time. So there's discharging through RB only. Then the capacitor, if you solve this, you will be getting 0.693 RBC. It is an off. So when you have to find out the total value, it will be TC plus TD. So then if you add this and this, finally you will be getting this value. So substitute it in a frequency 1 by T. So then you will be getting the value of 1.4 by RA plus RB into C. So this is about the frequency. So what is this duty cycle? The duty cycle for an astable multivibrator is defined as charging time by total time, that is on time by of total time. So by substituting charging time, so that is 0.693 into RA plus RB into C over the total time. So then you will be getting the percentage. So it will vary from 50% to 100%. That's what I told. So you have three cases. So that is less than 50%, equal to 50%, and greater than 50%. So this is about the astable multivibrator, and this is the end of module 4. Okay. Thank you.